excited to invite Niklas and Jonathan, and they're going to talk to us about a very beautiful book, which is very timely as well. And this is actually TruX, Jonathan and Niklas. I think we already talked about this briefly before you joined. So this is how it's going to go. So you're going to like tell us exactly what the paper is all about. But at the same time, we have there's going to be a question and answer section as well. And I believe that Jonathan will be the one to take care of that while Niklas actually did the presentation. So I think without further ado, I could just hand over to Niklas, but I would like you guys to actually introduce yourself as well. So like the entire TruX team can actually know you. So I think, like I said, we do a lot of things in like trustworthy software. So we'll talk more about that after the talk. But Niklas and Jonathan, yes. Yeah. Does Luciano want to say anything? Okay, good. All right. Awesome. Yes.
Yes, thanks for the introduction, and yeah, thank you for inviting us as well. Can you see my slides, by the way? We didn't check that beforehand.
Absolutely.
That's great.
Yes.
Okay, awesome.
Yes. Yeah.
So I will present the paper Chasing Shadows, Pitfalls in Security, LLM Security Research today for you, which will appear next month at NDSS. And about us, so yeah, I'm here with Jonathan, who is a PhD student at CISPA in Germany. I'm Niklas. I'm a PhD student at Max Planck Institute for Security and Privacy in Germany. And this work has been a huge collaboration between 15 different researchers from different institutions, so mainly from CISPA and MPI-SP, but we also have researchers from TU Vienna and Karlsruhe Institute of Technology, and also Sapienza University of Rome. Yeah, maybe let's start with some motivation. So why did we do this research? Why did we write this paper? So LLMs are, of course, a very hot topic at the moment in security and safety research. And since they are a very young method, or a relatively young method, I would say, they introduce some challenges, and we call them pitfalls, that can undermine the rigor, reproducibility, and soundness of research. And we know that there are some existing studies on pitfalls in ML security research, but we found that they mainly are concerned with classical machine learning methods. And we think that LLMs introduce some new interesting pitfalls, which the community needs to be aware of. So our goal was basically, we want to raise awareness about these pitfalls in LLM security research. And yeah, for a quick summary of our paper, so what we actually did is we identified 9 of these pitfalls in LLM security research. And then we collected a large number of papers from the top security conferences and the top software engineering conferences published in the last 2 years before we wrote this paper, which was last year. And yeah, the topics of these papers are either security or safety of LLMs, so security for LLMs, or also LLMs for security-related tasks like vulnerability detection or fuzzing, for example. And then the 15 researchers from our team reviewed all of these papers and looked for pitfalls in them in a process that I will describe later, and also assessed how prevalent are these pitfalls in these papers, and also we investigated the impact of these pitfalls on the validity of these papers. Yeah, for paper selection, so which papers did we actually look at? And so we have 72 papers in total. And how did we find them? So as I said, we looked at the top security and software engineering conferences, and we used some tools to do a keyword search. We just looked for some large language model related keywords. And then we did a manual review first of the abstracts of these papers, and then also maybe of the full text for some cases, to collect these 72 papers. And on the right, you can see the topics of these papers. So the most popular topic is security of LLMs. But then we also have lots of topics for using LLMs for security-related tasks, such as vulnerability detection, vulnerability repair, fuzzing, or secure code generation. Yeah, for the review process, so how did we actually assess these papers for the pitfalls? So first we prepared by doing some pilot reviews where we looked at a few papers and we looked for potential pitfalls. And then we wrote a pitfall guideline. So basically, this is a document which just describes for a potential reviewer, how should the reviewer read the paper, what should the reviewer look for when assessing a paper for potential pitfalls. And yeah, these guidelines can also be found in the appendix of our paper if you're interested. And then we went into the first review phase, which is the individual reviews, where we assigned 2 papers to reviewers to every paper. And then each of the reviewers assessed the paper for pitfalls and assigned 1 label for each of the pitfalls. And the reviewers did not see the reviews of the other researcher to make it kind of make it blinded to each other so that we have some more reliable results later. So this is the labeling process that the researcher went through, or the reviewer went through for one pitfall for one particular paper. So we first ask, let's say we have a particular pitfall, we first ask, is this pitfall even applicable to the paper? So maybe if this is a pitfall that is concerned with LLM training, then of course it can only be applicable if there was some LLM training in the experiments. So if this is not the case, we mark it as does not apply. If it's unclear from text, so we can't really say based on the paper, if this is applicable, we mark it as unclear from text. If yes, so if it is applicable, we ask, is this pitfall present in the paper? And again, we have multiple options. So if no, we simply the pitfall is not in the paper, we mark it as not present. If likely, so likely means we see a high probability that the pitfall is present in the paper, but we have no clear evidence. I will have maybe some examples on that later. Then we mark it as likely present. And if yes, so the pitfall is definitely in the paper, then we again ask, is it only present in parts of the paper, or is it present throughout the paper? And then we would either mark it as present if it was present throughout the paper, or as partly present if it was present through maybe one part of the experiments. And then we went into 2 discussion phases from that. So one discussion phase is for the 2 reviewers which were assigned to the paper. So there we have like a one-on-one discussion. And this was just to clarify disagreements between the 2 reviewers. And for the cases where there was some more ambiguity, so that could not be clarified through the one-on-one discussions, we moved them to group discussions where at least 10 of the 15 researchers from our group met to clarify these harder cases. And the outcome of this process was for a single label for every pitfall for every paper. All right, so now that we have the process down, let's actually dive into the pitfalls. So which pitfalls did we study and how prevalent are they in the papers? So we derived these pitfalls from the so-called LLM pipeline. So the LLM pipeline, in this case, we defined it as just an overview of the machine learning lifecycle. And we have 5 stages here. So stage 1, data collection and labeling, stage 2, pre-training, stage 3, fine-tuning and alignment, stage 4, prompt engineering, and stage 5, evaluation. And what we wanted to show is just that these pitfalls affect every stage of the machine learning lifecycle and can therefore compromise the LLM pipeline. And now I will go into each of these stages and describe the pitfalls that we found there. So stage 1 was the data collection and labeling stage. Here we have 2 pitfalls. The first pitfall is the data poisoning pitfall. And data poisoning means that since these LLMs are often trained on large fractions of the internet, it's very important to verify the integrity and safety of the data, because an adversary might place some data into the training data mix that can lead to negative outcomes for the users of these LLMs. So let's say maybe in vulnerability detection, an adversary might place some vulnerable code on GitHub or place it onto GitHub and then try to make sure that these LLMs do not detect this code when prompted later by some maybe open source maintainer. And the second pitfall in this stage of the machine learning lifecycle is the pitfall LLM-generated label inaccuracy. So since LLMs need lots of data to be trained, they also need lots of annotations for the supervised training stages of their training. And since labels can be very costly to produce, LLMs are often used to annotate data, or there's also this method which is called LLM as a judge, where one LLM produces some output and another LLM gives feedback on that output. And if you don't verify the correctness of this feedback or of these labels, this can of course lead to incorrectness in your labels. Then we have the pre-training stage of the machine learning lifecycle, where we only have one pitfall. This is probably the most well-known pitfall from all of the pitfalls. It's a data leakage pitfall. So what this just means is that there might be a potential overlap between your training data and your test data. And of course, this becomes very relevant with LLMs, because for the most popular LLMs, for the proprietary LLMs, we often don't know what's in the training data. So if we have a test data set that is basically publicly available, it's very hard to know whether this test data set has been in the training data of the model. Then we have stage 3, fine-tuning and alignment. Here again, we have two pitfalls. The first pitfall is called model collapse. And model collapse means that since LLMs are so data hungry during training, sometimes synthetic data is used for LLM training that has been produced by other LLMs. And this is actually kind of a natural and ongoing process, because much of the content that we see on social media, for example, is generated by LLMs. And if you use LLMs to train on this data, you get a larger and larger fraction of LLM generated data in your training data mix. And as we will see later in our experiments, this can lead to a amplification of bias, or also a degradation of data quality. Then we have the fifth pitfall, which is the spurious correlations pitfall. Spurious correlation means that there might be some features of your data which is correlated with the labels of your data, but it's not really in a causal relationship with the labels of your data. So again, an example for this would be, let's say you have a code data set and you want to learn to detect vulnerabilities in this code data set. Then maybe you have some keywords which are maybe related to memory operations that occur very frequently in the data points in the source code snippets that you label, that where you have the labels that these source code snippets contain security vulnerabilities. So in this case, a model could just simply learn to predict vulnerable if there is the presence of a specific keyword, and therefore achieve maybe a very high performance without actually understanding anything about detecting this vulnerability. Then we have the stage 4, prompt engineering. So here we again have two pitfalls. One is context truncation. So LLMs have usually fixed context windows, a specific number of tokens basically, and if your input is larger than this number of tokens, it gets usually truncated. And this might or might not be enough for your task, and therefore you should probably check it. Then there is the prompt sensitivity pitfall. So other researchers have also shown that LLMs are very sensitive to the choice of prompt, so also to the choice of system prompt, for example. And if researchers in their papers just use a single prompt, for example, to compare multiple different models, these outcomes might not be actually reliable predictions for the actual performance of the models, because one model might perform very well with a specific prompt, whereas another model might not perform well with this type of prompt. And you need to be aware of this phenomenon and optimize the prompts for your specific models. And then there is the stage 5, the evaluation stage. Here we have the last two pitfalls. The pitfall 8 is surrogate fallacy. Surrogate fallacy means that researchers generate findings for for a specific model or a specific model class, but then inappropriately generalize these findings to a larger model class or to other models. So an example for this would be, let's say you find that your model is that you have like a particular open source model maybe that performs very bad at a particular task, let's say hate detection. And then you write in your paper, LLMs are bad at this particular task. And then you would do an inappropriate generalization because there might be already some new LLMs, or there may come out some new LLMs later, which are better at that particular task. And then we have the last pitfall, which is called model ambiguity. And model ambiguity means that the details you provide about the models you used are insufficient for actually identifying which exact version or snapshot of the model you actually used. So an example for this would be, let's say you write in your paper that you used GPT-4 for a particular task. But for GPT-4, there are actually different snapshots that you can access via the OpenAI API. And these different snapshots might have different properties. So if you want to reproduce the findings, you need to make sure that you provide enough information for precise identification. All right, so now that we've went through all of the pitfalls, I will give you some information about the prevalence. So what did we actually find in our study? How prevalent are these pitfalls in the 72 papers that we have included in our study? So to explain this diagram, so we have a nice visualization where we have one row for every pitfall, and then we have 72 little rectangles, colored rectangles, and every rectangle is supposed to symbolize one paper. And the color of the rectangles is supposed to symbolize whether the pitfall was present in the particular paper. So we start with dark orange, means basically the pitfall was fully present. Then we have the normal orange with partly present. Then we have the light orange with likely present. We have gray for unclear from text. We have light blue for the pitfall does not apply to the paper. And we have dark blue for the pitfall is not present in the paper. And what you can immediately see from this figure is first that every pitfall applies to at least some of the papers, and every pitfall is present in at least some of the papers. And we have some clear differences between the different pitfalls. So for example, we have the model ambiguity pitfall, pitfall 9, which is present in 53 papers and also partly present in some of the papers. So it's basically more than 85% of papers are affected by this pitfall. So this is the most prevalent pitfall that we found in our study. But then we also have pitfalls like the LLM generated label inaccuracy pitfall, pitfall 2, that maybe has only been present in 8 papers. So there's only very few papers affected by this pitfall. And yeah, maybe just to give you some more of our findings. So one finding was that every paper was affected by at least one pitfall, which is quite interesting. And then, yeah, our most prevalent pitfalls were model ambiguity, data leakage, and surrogate fallacy. These numbers that you are seeing here, so 86% means 86% of papers were affected by this, and affected stands for the pitfall is either present, partly present, or likely present. And we also have like the least prevalent pitfalls were model collapse and label inaccuracy with only 13.9% and 15.3%. And then we also, during the labeling process, we also captured whether, let's say, a paper was affected by a particular pitfall. We also captured if the paper acknowledged the pitfall or discussed the pitfall in the paper. And we call this awareness. And what we found is that there's overall quite a low awareness about these pitfalls. So only 15% of affected papers actually discuss the possibility of these pitfalls in their papers. And interestingly, we even have 3 pitfalls, model ambiguity, model collapse, and data poisoning, where actually not even a single paper discussed the presence of these pitfalls. But we also have two pitfalls, LLM-generated label inaccuracy and context truncation, where the community seems to be quite aware already, and it seems to be discussed, and sometimes there are also remediation actions employed, which I will also talk about later. Then we also looked at prevalence by research topic. So what you can see here is the average pitfall presence over the different topics of our papers. And yeah, we can see some differences. We can see that papers on the topics of vulnerability repair and vulnerability detection seem to be quite affected by these pitfalls, with vulnerability repair even having 28% average pitfall presence. And then we also have topics like secure code generation and fuzzing with below 20% average pitfall presence. But all topics are basically affected. We can also say that. Okay, so now I've talked about how prevalent these pitfalls are. We also implemented some experiments, some case studies to investigate the impact of these pitfalls. So we asked, how can these pitfalls affect the validity of the research findings? And I will present 3 of the case studies we did here. We have 2 more in the paper. And we selected these case studies based on the pitfalls which were most prevalent in our paper. And the first case study I will talk about is about the model ambiguity pitfall. So as a reminder, model ambiguity means that that is important to give enough information about the models you use that you can precisely identify the exact version or snapshot you used. And the experiment we did to investigate the impact of this pitfall goes like this. So we re-implemented a hate detection method from an SMP paper, where they had a data set of tweets which were labeled as either being hateful or normal from X on a particular topic, on the COVID-19 vaccine topic. So quite spicy topic on X at least. The LLM had to answer a series of questions to determine if the text is hateful. And then we tested 3 different snapshots of the GPT-4 model. So here you can see the snapshot identifiers on the task, or we tested them for the performance on identifying whether a text is hateful, basically. And the idea here is that if you would see differences in the performance, this would show that it's very important to provide the exact identifier. And here you can see the results. So we have accuracy, precision, and recall for the 3 different snapshots. And yeah, we can see that the accuracy, interestingly, varies between the 3 different snapshots. So we have from 77 to 88% accuracy. And if you look at recall, we have an even more drastic difference. We have 41% of recall for one of the snapshots and 82% of recall for another of these snapshots. So in this case, the bottom line is that it's quite important to report the exact information to identify the exact model you used. But of course, this also varies a lot from task over tasks and data sets and models. So you should probably test this for your particular case as well. And then we have another case study on the same pitfall of model ambiguity. So we also looked at the impact of quantization. So as a reminder, so quantization is a technique to make a model more efficient by storing the weights of the model with fewer bits, basically. And we tested the impact of quantization using a so-called secret key game. So in the secret key game, the model is given a secret key in the system prompt with instructions to keep the key a secret, basically, to keep it confidential. And then we used a suite of prompt-based attacks to get the model to give out the secret key, basically. So the attack was successful if the key appears in a response of the model. And we used 1,000 attack attempts per model across 16 different attack types. So these are attacks like jailbreak attempts, or attaching some adversarial suffixes to a prompt, like some letters, for example, and attacks. Yeah, these are just 2 of the 16 attack types. And then we use the setup to test different llama models at 2 to 8-bit quantization to see if the attack success rate of the secret key game varies between the quantization levels of the same model, basically. And here again, we have quite interesting results. So maybe look at the first row of this table. So we have the model code llama 7 billion, which was provided by OLlama. And we have the quantization level. So we have 2 to 8-bit quantization. Also on the right, we have no quantization. And then you can see the attack success rate over these different quantization levels. And what's super interesting to us is that the attack success rate varies quite drastically with the quantization level. So I mean, at 2-bit quantization, you can definitely understand why this is happening. So 2 bits is very few bits to store weight. So we have 70% attack success rate, but even between like maybe 3-bit, 4-bit, we have still variations between the attack success rate between the different quantization levels. So it's very important that if you use quantization, or if you use a quantized version of an LLM in your experiments, and this is often the case if you use open source models, because like popular provider of open source models often provide quantized versions so that they can run on consumer hardware, maybe. So it's very important to report this in your paper so that the experiments are reproducible, basically. Then we have another case study on a different pitfall. So this is the model collapse pitfall. As a reminder, the model collapse pitfall was when you train on data that has been also generated by an LLM, so synthetic training data. Here we used a Gwen model, and we fine-tuned it on 50,000 Python code samples. And then we used the fine-tuned model to generate synthetic samples. And on the outputs of this on the synthetic outputs, we fine-tune the next iteration of the model. And then we repeat this basically for 10 generations, and we measure the perplexity using the original model. So perplexity is a measure that basically measures how surprised or how uncertain the original model is for these 50,000 generated, or for these generated, I don't know if we generated actually 50,000. Maybe Jonathan can answer this later in the Q&A. Where for the generated samples, yeah, we measure the surprisingness or uncertainty of the model, of the original model, for these new synthetic samples. And we can see the results here. So we have one distribution of perplexity for each generation that we trained. And the more orange the distribution is, the later we are in this generation process. And we can clearly see that the distribution moves to the right, and also the variance of the distribution gets bigger. And what this means is that the perplexity of the original model increases with each generation. So the model becomes less certain and more surprised. And also the variance grows over generations, which we interpreted as an increasing instability. So this is just an interesting pitfall because of this phenomenon that large amounts of content of the internet are generated by LLMs. And this is definitely something the field in general has to keep in mind if internet data is used for training. And then we have 2 further case studies, one on the data leakage pitfall and one on the context truncation pitfall. I omitted this from the talk to stay within the 30 minutes, but you can either read it up in our paper, or you can also ask during the Q&A. So I have extra slides for this in case you're interested. And then we also developed some guidelines. So we, of course, wanted also to give some advice on how researchers should handle these pitfalls. And we have these guidelines up on a website, which is called LLMpitfalls.org, which we are planning to update regularly, and where you have a very extended version of these guidelines. And of course, these guidelines are also part of our paper. And I have some of them here, but not all of them, because we have quite a few. And what we first can say is that not every of these pitfalls can actually be addressed, right? So for example, data poisoning, it's oftentimes either impractical or sometimes even impossible to verify that your data is free from data poisoning if you take it from the internet. So let's say you take a code data set from GitHub. It's basically practically impossible to show that there's no security vulnerability in a specific software repository. So what researchers in these cases should do is they should just acknowledge that the pitfall is potentially there, because maybe it is relevant for practitioners to know that it could potentially be there, or also for other researchers, and discuss the pitfall maybe in a short paragraph or something. But more like sometimes you can't actually do more than that, because even if you would try to verify a specific subset of your data set, you could not show that the whole data set is free. Often not show that the whole data set is free from this pitfall. But for other pitfalls, there are very concrete best practices. So for example, for the model ambiguity pitfall, just report exact model versions, just give enough information that you can actually identify the exact version you used. So for open source models, this would mean, let's say you take a model from Hugging Face, you can provide the exact commit hash of the repository of the model. You can provide the date that you accessed the model. You can provide the URL where you access the model, and so on. You can provide the quantization level. You can, if you use a proprietary model, you can state whether you access it via the web interface or the API. You can give the exact identifier. Again, you can give the date of access, and so on. Yeah, for data leakage, there's also some advice. So a simple test is, if you know the training data cutoff of a particular LLM, you can, and you have a data set that was maybe released, you have a data set where parts of the data was released before the cutoff and parts of the data was released after the cutoff. This would be a way to test whether there is some performance difference between for the data that was released before the training data cutoff and for the data after the training data cutoff. And of course, there are also ways to check whether data is or might be in the pre-training data, but these are most of the time not. You don't have a clear proof that data was or was not in the pre-training data. It's more like you have some indications. Yeah, for context truncation, of course, you can check the context truncation window of your LLM, and then you can, maybe if you have a data set, you can calculate the number of tokens that your data usually takes, and this way also see if maybe you can test a statistically significant subsets, and then you can maybe make a statement about how likely it is that your task stays within a particular context window. And similarly for LLM-generated labels, if you generate labels using LLMs, you can also collect a statistically significant subset of these labels, and then compare them with human annotated labels for the same data, and thereby assess the quality of your generated labels. All right. So as a conclusion, so every paper we investigated has pitfalls, even carefully conducted research. So we are not trying to say these papers or these authors did anything wrong or did a bad job. I mean, some of these papers have also been written by co-authors of our paper. We just think that it's a matter of raising awareness, right? I mean, these are relatively young methods, and there are pitfalls which are just not very well known. And if we raise awareness about these pitfalls, this might lead to researchers being careful about them, and then there might be fewer pitfalls in papers in the future. And also, of course, the fact that there are pitfalls in every paper could also be due to the fact that there are some pitfalls which are just unavoidable. So in these cases, it's also worth it to raise awareness, because then researchers can discuss these pitfalls even if they can't do anything about it. And our catchphrase here is, from chasing shadows to reproducible, trustworthy research, which is our vision for the future. All right, so thank you for your attention. Yeah, we will be happy to answer any of your questions. If you want to check out more about our work, we have here some links in the QR code to our website. And you can also reach out to us via email if you have further questions, or if you want to just discuss any interesting research questions or something like that, then we're always happy for that.
Awesome. Thank you. Thank you very much. Thank you, Niklas. And so are there questions?
We'll request first.
Maybe you.
Yes.
Oh,
yes.
sorry.
So thank you very much.
Oh,
Can we just have, the case study about, data leakage? Can you present it quickly for data leakage?
Yes.
Thank you.
Yes. So for data leakage, we focused on the PrimeVol dataset, which is a popular dataset for vulnerability detection. So this is a dataset which contains source code functions in C and C++. And then it is basically labeled for whether this function contains a security vulnerability. And then we tested 4 proprietary LLMs and 3 open source LLMs with basically half for each of the functions in this dataset. We also looked at the fixed commits for these functions, so where the vulnerability was eventually fixed. And then we took the commit messages and these functions and cut them basically in half. So we only used the first half of these commit messages and functions, gave them to the LLM, and asked to reconstruct the rest of these commit messages and functions. So we basically attempted, maybe if the model, or the idea was, if the model can, of course, completely reconstruct these commit messages and functions, it's evidence for this data set being in the training data of these models. And interestingly, we got actually 0 out of 100 matches. So our intuition was, because this dataset was available for a long time in the internet, it should be in the training data mix. And these are just very popular. It's based on very popular open source GitHub repositories. So we thought this should. Our intuition was it should be in the training data, but we actually got 0 out of 100 matches for all models. And we even, so there is this hypothesis that that you can fine-tune models to not show that they have been trained on particular data. So this is due to instruction fine-tuning of these models. And there is a adversarial attack where you can try to fine-tune a model to make it better at completing data that was in the training data. So what we did is we also fine-tuned a GPT 3.5 model on 1,000 commit messages to reconstruct them. And then we tried again on a held out test set, but even with this setup, we got 0 out of 100 matches. And then we went further and we looked into common crawl. So common crawl is kind of an index for the internet, let's say it like that. So it's like a crawl of the internet, or of large parts of the internet, where that researchers can use if they want to pre-train an LLM on a super large data set. They can use this to get like kind of a snapshot of the internet. And for GPT-3, there is a paper which lists some of the common crawl snapshots they used, and GPT 3.5 is an advanced version of the GPT-3. And so we also looked into these common crawl snapshots, and we did not find any PrimeVol related content there. So in this particular case, counter our intuition that LLM should have been trained on this data set, we actually did not find any evidence of memorization. So this doesn't mean that it's no proof that this data set is not in the training data, but at least we haven't found any evidence for it, which was interesting to us. So yeah, that was the data leakage case study.
Thank you very much. Just a quick concern that I have with the fine tuning. So we have an experience here in our team that the more epochs you have in the fine tuning, the more likely you will reveal actually memorization. But this your case, there seems to be a pitfall since you did not disclose how many epochs did you use.
I mean, hopefully in our paper we disclosed how many epochs we use. I'm not. I mean, if not, you can write a paper about the pitfalls in our paper.
The pitfalls of pitfalls.
Going back, I have another question related to the data poisoning. I do, I had this, when you started to present, I was like, oh, how will you ever demonstrate that there is or there is no poisoning? And then your conclusion is, okay, this is not something that you can action on. But then again, I look at your graph, and then in the graph, you do have clarity about some papers. Yes, this one. You do have some papers, you say it's present, others you say it's not present. So how do you evaluate, given a paper, that there was and there was no data poisoning pitfall?
Yes. So, okay, if I remember correctly, we defined it as the paper uses data sets collected from the internet without validating the labels, without validating the data, and it's a task where data poisoning is relevant. So let's say you are you have a task like vulnerability detection where data poisoning is actually relevant, and you're using a data set from the internet to train your model, and you're not verifying that there's no data poisoning in the data set, then we defined it as being present, even though we don't have clear evidence that the data was poisoned. It's in this case just a matter of how we defined it.
Okay, thank you. So it's related to the tasks. It's
yeah.
So
yes,
it's possible that you may have underestimated some tasks with respect to data poisoning as well.
Yes.
So the lot of blues here actually could be very optimistic.
Yes.
You have many. Yes. Okay, good.
I mean, so does not apply. Let's say there's no training going on, then of course it does not apply, right?
Yes.
Or it can also apply in the sense that if you use a pre-trained model, this could also be poisoned, right? So,
yes.
But I think we probably clarified that in the paper. I'm not sure right now how we handled that particular case. Yeah.
Okay. Great work. Thank you. Maybe one last question. I see that you discussed about topics, you discussed about every paper, but did you discuss about fields? What do you think between software engineering and security? Do you feel like software engineering papers have more pitfalls than security papers?
Okay, so we haven't looked at that in the paper, but of course I can give you my experience based on these results. So as you can see in these topics, so the topics marked in dark blue are basically security of LLMs and Gen AI safety. And these are papers which have been presented more on security conferences rather than software engineering conferences. And we have the topics like vulnerability repair, vulnerability detection, secure code generation, and fuzzing, so the light blue topics, which are more part of software engineering conferences. And as you can see, both the most prevalent topics and the least prevalent topics are from software engineering, and security seems to be somehow in the middle. And this matches my personal experience very well, because my main research topic is machine learning for vulnerability detection, and I see a lot of pitfalls in the machine learning for vulnerability detection papers. So this also was one inspiration for actually doing this research. So I think parts of the software engineering conferences are the papers where you can find the most pitfalls, but then others like fuzzing, maybe you have the least amount of pitfalls.
Okay, thank you. That's it for me.
Any other questions?
I do have a couple.
Yes. Two actually, not taking.
So the first one is about the second vulnerability, which is the LLM generated label inaccuracy, if I remember correctly.
Yes.
And so there is like a field of the traditional, let's say, field of machine learning, which is kind of like weak supervised learning, no? Learning from weak labels, this kind of stuff. So basically you have some labels which might or might not be accurate, but on average you kind of learn. And this seems to be like the obvious way of using labeling in LLMs, no? Like you label them and it might or might not be correct, but on average it's better than no label. But then it's a pitfall, so I assume, and it's like what I'm wondering, do people take it like at face value and treat it as, let's say, were hard labels, or do you think it's a problem per se of using weak labels for training?
I think it's a problem if the researchers don't investigate first the correctness of these labels that they produced. So first you want to know how good is the correctness of these LLM generated labels, right? Let's say only 10% of them are wrong. And then if you know this number, you can investigate the impact of this incorrectness on your training procedure, right? So as you said, there is definitely some research that shows if you have a massive amount of almost correct labels, this can be beneficial to your model. But in this case, so let's say you do that, you generate labels using an LLM, you investigate the correctness of your labels, and you also investigate the impact of this on your whole setup, then I would not say, or we would have not classified this as a pitfall being present, because if the pitfall is correctly remediated, it's not present, right? Even though they used LLMs to generate labels. It's only present if they do this and don't check it. But even in this case, of course, it could be that it is still not a problem, but we don't know if it's not a problem if they don't do this work. Would be my answer to this.
I see. Makes sense. Thank you. And the second question is about data poisoning. So you said it's basically undetectable whether there is poisoning. I'm wondering if and basically you treat it as in a very conservative way. So if there might have been poisoning, I treat it like if there might have been poisoning and you didn't check, I treat it as a vulnerability. Did you, in your experience or any member of your group, actually see any data poisoning happening? Or is it, let's say, we're treating it in a very, this could happen, so it's better to be safe. But like, do you have an example of, let's say, data that have been somewhat poisoned or like you could define as poisoning? Ever seen in your life, kind of?
So I've never seen an actual instance of data poisoning, actually.
No, me neither.
Okay, okay, thank you. But it's like what I would like to research on. So like it's interesting to see if someone has ever, let's say, seen anything happening real life. But yeah, I agree. It's like still a problem. So it wasn't a critique.
I mean, I think especially for vulnerability detection, it's definitely possible to do to poison data, would be my guess. So you could try to plant a vulnerability into an open source package and then try to plant it in a way that it's not detectable by LLMs, right? That would be something someone could do, but I mean it's theoretic because I don't know any actual instance where it happened.
Awesome. Any more questions? Any more questions? Yes.
Okay, I don't have a question, but I would like to discuss insights about the data poisoning pitfall, which seems to be hard to solve. So actually, one of the problems of the dataset poisoning is that there's, huge corpus of datasets which cannot be verified. The path to verify them is complex. For example, in the field of software engineering, code data sets, they are huge, and they link to GitHub repositories, right? And I was wondering if the curation could be collaborative. So if we could maybe join forces and make the curation collaborative and trustworthy so that we can certify the data set. Like we have kind of a certification where kind of statistics on the data sets, metrics based on some properties. Because for the code, we have already tools that are capable to detect vulnerabilities. So we can say, okay, this data set is free, from or certified at this percentage given, from this tool, actually, this detection tool. this maybe could help kind of have a.
I guess, yeah, my opinion for that would be that it could definitely help if you have good tools, right? I mean, for vulnerability detection, it's quite interesting because there's a lot of research about that it's very difficult to prove that code is free of vulnerabilities, right? I mean, probably for some vulnerability types you could have, you can have certifications, and yeah, then it would probably be beneficial. But when you say collaborative, do you mean collaborative between the researchers and the maintainers of the software, or do you mean collaborative in a sense that it's yeah, how do you mean the collaborative aspect of this?
I mean, by collaborative, I mean all those people using the data sets. I mean, those people doing the curation, whether they are researchers or other people just working on it. Yeah, here the main layer would be, it should be verifiable. I mean,
yeah,
at least the process of certification should be trustworthy at the end so that people can trust it.
Yeah.
So otherwise, you just need to trust the dataset provider, which might be poisoned, right?
Yeah. Yeah, my intuition for vulnerability detection in particular would just be that it is super hard to generate some certificate that has a good power of what it's saying, right? I mean, you can make maybe for some very specific vulnerability types and some very specific software, you can maybe make some good statements that there is some specific likelihood of vulnerabilities being in there. But in general, I think it's quite hard to say that the code is vulnerability free. Yeah, I think it's just a huge challenge, but it's still interesting. I mean, because it's such a problem, or it's hard, that makes it also interesting, I think.
Thank you.
Maybe one last question. So it's about the spurious correlation.
Yes.
So normally, one problem you have in a data set, especially with LLMs, is that as much as you can divide training and test, there can be some regularities basically that will be there regardless. So let's say if every time, like in the stupidest way, every time you have like some malicious code, you have a comment before, like regardless of how you cut it, the LLM is gonna find out that there is a comment before, but I think it's like zero causal connection to what you will find. My understanding from what I've seen is that sometimes you have a model that works, but then you test it. Rather than splitting training and test in a different way, you train it on a completely different data set. So you try the same approach on a different data set, or you try the crossword functionality, and it doesn't work. And that for me is because basically the two data sets are different enough that it's actually what it should be. So training and test being independent. Do you think the problem is that there are literally sometimes on some task free data sets. So it's not like you can do much of it. Do you think you can just, let's say, like, what is the solution there? Like, how do you solve the problem apart from like just assessing it once on the second one and continue?
Yeah. So one possibility, let's say you don't have multiple data sets, you can still do some things to against spurious correlations. So for example, there is this whole literature on robustness, right? So you can do some adversarial attacks based on possible spurious features. So let's say your model learns specific the connection between specific superficial elements of the code, like variable names and labels. You can employ attacks that change all of the variable names and see if the performance is still the same. And there's a whole suite of possible attacks that you can do, or robustness checks that you can do, which try to get you closer to estimating the actual capabilities of the model on your task that is independent of any superficial properties. But this is, of course, only like empirical, so you can only get closer to the truth, but you can it's probably for these large models, which are super complex, it's very hard to prove that they actually don't rely on spurious features. But this would be some practical things, would be to use robustness methods for this.
I think makes sense.
Awesome. All right. So we have more questions. I have quite a lot, but I'll give the floor to other people. More questions? We have like 5 minutes to the end of the meeting. Any more questions? Laura, you look like you wanted to ask a question. No? Okay, no. Okay, good. All right, yeah, yeah, you have a question?
Yes.
Please.
Thank you for your presentation. It's very insightful about the pitfalls with LLMs. I have one question, like in model ambiguity, you talked about snapshots and about like providing as much information as possible for reproducibility purposes. But is non-determinism, for example, part of model ambiguity concerns? If yes, let's say we have like the percentage that you showed earlier for the same snapshots. And a few months later or years later, we reuse them while the model like has maybe evolved. Like, do you think that we might have also slight changes because it was at a time where maybe you can have those results, but maybe like weeks later or months later, like another snapshot like could give better performances than the rest. Like, what do you think about it?
Yeah. So I think in terms of a different snapshot gives different performance. I think we capture this phenomenon quite well, right? We think you should give the most information possible. So if you use a different snapshot and get different performance, this is covered by the model ambiguity pitfall. But what you mentioned, the non-determinism of a particular snapshot is, I think, not covered by this model ambiguity pitfall, because as you said, maybe you can use the exact same configuration and you get a different result. But what you can do against that phenomenon is use statistics to your advantage, right? You can repeat your experiments a certain number of times, and then you can make a statistical statement about your results, how significant they are, basically. So simply said, just you repeat the same using the same configuration. You repeat it multiple times and see how much does it vary, and yeah, then you can. This is a way to deal with the non-determinism. But of course, I mean, something you've also touched on is what we can't do anything about is, let's say we have a specific configuration of a proprietary model. Let's say we have the exact identifier, the exact date, how you access the model, we have everything. But of course, OpenAI or some company like that could still decide, okay, we change something about this model behind the API, right? Maybe there's some political reasons why they want something to not appear in the output, so they put some filter on top of it, and then the output changes. And this is probably happening. And yeah, we can't do anything about it. Would be my guess. I mean, you could even there you can maybe acknowledge this risk in your paper and say you might get different results if they change anything about it. But I mean, the solution might be use open source models. Yeah.
Thank you.
Awesome. So I think the clock is reminding us that we have 2 minutes to leave here. But maybe just one last question from me. Yeah, nobody had a question. Nobody. Good. Okay. Yeah. Maybe this is probably a soft one because I think I'll maybe reach out to you later for the more difficult ones. But this direction is about the self-reporting. So I want to ask about this self-reporting pitfalls. Do we actually trust them, or are there incentives for people to actually indeed want to do self-reporting? And is it comprehensive from your analysis? Like just give a very short answer.
So by self-reporting, you mean that
exactly
should
self-reporting
discuss
exactly like the papers discussing the pitfalls themselves.
I mean, that's an interesting question. I mean, let's say for the data leakage pitfall, because so many people seem to be, at least in the researchers I talk to, people seem to be aware about the data leakage issue, right? And if I, for example, review a paper and I see a data set that has been released 10 years ago, and they use this to draw a conclusion, if the paper does not have a section about the possibility of data leakage and how they deal with data leakage, I mean, I immediately have a bad feeling, and I would in the review I would definitely ask about this and maybe question or just ask for a section or about a statement about data leakage. So in this case, I would say there are incentives for researchers to self-report because if the reviewers are aware, then they will ask for this. So it is definitely better in these cases to have some content in your paper about it. Would be my guess. For the pitfalls that where people are not aware about it, probably it would be the incentive to not talk about it. But yeah, if we raise awareness, there should be a growing incentive to self-report.
Awesome. Niklas, thank you so much. Jonathan, we really appreciate it. Thank you very much. And again, I'm sure we are probably going to invite you some other time, but thank you so much for your time. All right.
Thank you for inviting us.
Awesome.
Thank you.
Awesome.
Goodbye.
Yeah, bye-bye.
Bye.
Yeah, bye.
Bye-bye.